Hello. In this video, we study properties of determinants. We learn how to find determinant of a product of matrices and how to find determinant of the inverse of some matrix. Okay, so let's talk about determinant of a product of matrices. Suppose that you have two matrices A and B of the same size, of course, and you can find determinant of A and B is equal to determinant of A times determinant of B. Means determinant of a product is the product of determinants. Such property helps you to avoid huge computation in here, A times B. Okay, so you just need to find determinant of A as just a number, and then determinant of B, and then just, take product. Okay. It's very easy to prove this property, so I encourage you to read in the textbook. The proof is based on elementary matrices. Okay. Let's apply this property to find the determinant of the product for the following matrices. A is 1, -2, 2, 0, 3, and 2, 1, 0, and 1. B is 2, 0, 1, 0, -1, -2, and 3, -1, -2. So firstly, we need to find determinant of A, right? The determinant of A can be found, you have different methods already, you know how to do that. But again, we in the previous video, we studied how to use elementary operations, right, to find determinant. So I will use that right now. I will multiply the first row of A by -1 and add to the third. Okay, so I have 0 in here, 3, 2, 0 in here, 2, and -1. And then this is equal to determinant of 3, 2, 2, -1. And that is 3 times -1 minus 2 times 2. And you have -7. Okay. And then you can find determinant of B. Again, you can see 0 in the B, right? But now I will use column operations because I see 1 in here. You see? I see 1 in here. So I multiply the third column by -2, add to the first. Don't forget that, when you solve system of linear equations, we don't have right to use column operations. But for determinant, yes, we can use column operations, and we don't change the determinant of the original matrix. Okay, I mean, in the sense that, if just you multiply a column by scalar and then add to the other column, so the determinant will be the same. So I will multiply the third row by -2, add to the first one. So let me rewrite the third and the second column, right? Okay, so I multiply the third column with -2, add to this, I get 0, -2, I have 4 in here, and then -2, I have 7 in here. So you already have 2 zeros. I delete this. The position of this guy is 1, 3, right? 1, 3 are of the same parity, so the determinant of this equal to 4, -1, 7, -1. I mentioned this because if these two indexes are not of the same parity, so you need to add negative, right, on the top by the definition of the determinant. And this is equal to 4 times -1 minus -1 times 7. You get -4 plus 7, which is 3. And then from here, you can find determinant of product equal to product of two determinants. That is -7 times 3, which is -21. As a consequence of the previous theorem about the determinant of product of matrices, we have the following. Suppose that A is a square matrix of the order n and C is a scalar, just a constant. Then determinant of CA equal to C to the n determinant of A, right? It's pretty easy to prove this because, what is C? C in this case can be considered like Cin, right? So I have determinant of Cin A is equal to determinant of Cin times determinant of A. But determinant of Cin, you have all entries on the main diagonals, right? So you have C in here. So this determinant is nothing but, C to the n, right? That of A. I remember in the previous video we studied one property of determinant, like if you multiply a row or a column by a scalar, then you can take the scalar out, right? Or determinant of the new matrix should be equal to scalar multiple, of that scalar and the determinant of the original matrix. So in this case, if you multiply all rows, all entries in here, right? Or all rows by a scalar. So you have n times, that means you have C to the n, okay? So let's apply this property to solve the following determinant. Let's find that of 10, negative 20, 40, 30, 0, 50, negative 20, negative 30, and 10. Sometimes you have to work with such matrices, like entries are really big numbers, right? And in this case, you can see all entries of this matrix are scalar multiple of 10, right? Of 10. So you can take 10 out. Okay, you can take 10 out. But what is when you take 10 out, so you have to write 10 to 3, right? Because the matrix is 3 by 3. And then I have 1 in here, negative 2, 4, I have 3, 0, and 5, and I have negative 2, negative 3, and 1. Okay, and then you can evaluate the determinant of this matrix as usual. So you do whatever you want, right? We know several methods. And now I see I I already have 1, 0, so you can expand that, using using row elementary operations. But now this is 3 by 3 matrix, so let me apply the diagonal method. Okay, so I have 10 to cube is 1000, and I have 3 terms with respect to the main diagonal, right? So 101 is 0 plus negative 2, 5, and negative 2 in here. So I have 4 times 5. Negative 2 with negative 2 is 4, okay? And then another is 3 with negative 3 and 4 right here. So plus 3 times negative 3 times 4. We still have another 3 terms, but with respect to the odd diagonal, right? So I can write in here negative 2 times 0 times 4, and then minus 1 times negative 3 times 5. You see this one with 0 in here, and the last one is negative 3 times negative 2 and 1. So you just simplify all this, you get 100 times 5, which is 5000. Okay, you see, sometimes that helps to avoid big computation. Because if you apply, a direct computation for this determinant, yeah, of course you need to work with 10s, 20, or 40 or whatever, big numbers. Okay, we have different properties of determinant of product, right? Let me rewrite this. That is that of A times that of B. But again, right, we don't have a similar property for sum, okay? We don't have this. That B. Never, okay? Never do that. There are a lot of interesting things regarding determinant of sums. many interesting things, and even we have some open problems regarding determinant of sums, but we don't have this identity. Okay. All right. Now let's talk about determinant of the inverse matrix of some matrix. Okay. I think we were talking about that a little bit at the end of one video about determinant. Let's say if we have matrix A, right? That is the size of n by n. And we were talking about determinant of A is not 0. Then, let's say if, then A is invertible. Remember that, right? We actually we prove this property when we study determinant and elementary operations. Because we use elementary operations to convert A into row echelon form, right? And if that row echelon form has all non-zero entries on the main diagonal, like this, if all entries in here are non-zero, then the determinant of A is just product of all entries on the main diagonal, because this is triangular matrix, right? So if the determinant is not 0, then A is invertible. That's it. Okay, because all entries are not 0. And of course, if A is invertible, means all entries in here should be non-zero, right? So you have determinant is different to 0. So actually, this is if and only if. Okay, and that is one way to determine if a matrix is invertible or not. Don't forget that. And we learn about invertibility of a matrix and the solution set of some system of linear equations, right? Let's summarize them and then we move to examples. Okay, so let A be a matrix of n by n, right? An n by n matrix. Okay, then the following statements are equivalent. The first one, A is invertible. Okay, the second, the system AX equal to B has a unique solution. Okay, for every B, of course, for every B. And we can find that solution using the inverse matrix, right? 3, AX equal to 0 means the homogeneous system has only trivial solution. That means, only 0 solution, right? And A can be written as the product of elementary matrices. We know this already. Right? And of course, the last one is determinant of A is not 0. So you see, sometimes if they ask us to consider the solution set of some systems, right? And the coefficient matrix is square, so you can use determinant to see that. You don't have to solve the system, but you can calculate the determinant of the coefficient matrix. And if the determinant is not 0, so the system has a unique solution. Does that make sense? Thanks to this, determinant is very, very useful, and I will tell you, yeah, that is very important. Okay. All right. Let's consider the following example. We have the following system: 2x2 minus x3 equal to -1, 3x1 minus 2x2 plus x3 equal to 4, and 3x1 plus 2x2 minus x3 equal to -4. And they ask us about the solution set of this system, right? The solution set. So, you just need to check the determinant of the matrix A, the coefficient 1, 0, 2, -1, 3, -2, 1, 3, 2, and -1. You don't care about B, right? You don't care about this vector. You just need to care about the determinant of A. So A can be, I have 3 and 3 in here, so I just multiply the second row by -1 and add to a third, right? Add to a third. So I have that is determinant of 0, 2, -1, I get 3, -2, 1, 0, 4 in here, and -2. And this is negative because 3 has the position 2, 1, right? They are not of the same parity. So we have negative in here. And 2, -1, 4, -2, okay? And what is that? That is -4 plus 4, which is 0. So that means the matrix A is not invertible, right? It's not invertible. Since A is not invertible, the original system should not have a unique solution, right? Okay, that is my conclusion, right? The system should not have a unique solution. So what does it mean? That means we still don't know. We still don't know about, the solution set. We know exactly that, the system should not have a unique solution, but we still have two other cases. The first case, no solution. And the second case, infinitely many solutions, right? But of course, in case if they ask us to determine, right, how many solutions this system has, so we might continue solving this. But they just ask us about, maybe, okay, about solution set, or maybe they ask us more specific question. Which of the, does this system have a unique solution, right? Let's say this. Does this system have a unique solution? So your answer is no, right? Because the coefficient matrix is not invertible. But in case if they just ask about, the solution set, like how many solutions does this system have? So you need to continue, right? But if the coefficient matrix is invertible, so you can say right away, only one solution. Okay, so I will not solve this. I think you can check this yourself because we know how to solve system of linear equations. Okay, now we didn't say anything about the determinant of an inverse, right? But it is also pretty easy. If A is invertible, right? So we have A to -1 times A is what? So this is determinant of identity, right? Which is 1. Is that correct? At the same time, you might apply determinant of product is equal to product of determinants, right? And that is 1. So from here you can see determinant of A to -1 means of the inverse is equal to 1 over that A. And that is that I can write this way to -1. Okay, that of the inverse is equal to the inverse of that. And so you don't need to find the inverse matrix A to -1, but you still can find the determinant of the inverse using the determinant of the original matrix. Okay, again, right, I have to mention, because the matrix A is invertible, so that's why determinant of A is not 0. That's why you can divide by determinant of A. All right, so to finish this video, let's solve the following example. Let's find determinant of the inverse of A if A is equal to 0, 2, -1, 3, -2, 1, and 3, 2, and 1. Okay, so let's find this. I need to find the determinant of A. I write that of A equal to 0, 2, -1, 3, -2, 1, and I multiply the second row by -1, add to the third. I have 0 in here and 4 and 0. Okay, so since 3, the position of 3 is 2, 1, they are not of the same parity, so when I simplify that, I have -3 and then multiply with what? 2, -1, and 4, 0. Okay, so this is equal to -3, and here I have 2 times 0 plus 4 minus with the negative is plus, so that is -12, which is not 0. Perfect. Then A is invertible, right? A is invertible, and of course then we have that of A to -1 is 1 over -12, which is okay, -1 over 12. That's how we can use determinant to find the inverse, the determinant of the inverse. Okay, so I hope that the video is clear enough, and I think all properties in here are very, very natural, very easy, but there are a lot of useful application, especially this theorem. Don't forget that. So this theorem is some kind of connection, right? We combine almost everything about system of linear equations in this theorem, about the coefficient matrix, determinant, invertibility, the solution set, or even homogeneous system. Okay, so thank you, and see you in the next video.